Welcome all my dear student of SYBSc physics class. In this lecture we are going to solve some important problems regarding to geometrical optics which are very important for exam point of view. So first problem is like this. Calculate the focal length of double convex lens for which the radius of curvature of each surface is 25 centimeter. Radius of curvature. Solution given. First R1 is given. What is the problem? Listen the problem carefully. In a problem we have to calculate the focal length of double convex lens. Suppose this is double convex lens and we have to calculate the focal length of this convex lens, focal length. Now here radius of curvature of both the surfaces, for this surface and for this surface, for first and second surface, radius of curvature is given. R1 is what? 25 centimeter. If R1 is 25 centimeter, obviously R2 is minus 25 centimeter because one of the radius is negative. Here refractive index, that is mu, is also given 1.5. It has no unit, it is the ratio. Okay. So in order to find out the focal length of a convex lens whose radius of curvature is 25 centimeter and whose refractive index of the material is 1.5, we have to use the formula 1 upon F is equal to mu minus 1 in bracket 1 upon R1 plus 1 upon R2, sorry, minus R2. This is nothing but lens maker formula. Now what we have to do? We have to substitute only value of given data. Therefore 1 upon F is equal to 1.5 minus 1 in bracket 1 upon 25 plus 1 upon minus 25. So not plus minus. So we have 1 upon F is equal to 1.5 minus 1, 0.5 in bracket 1 upon 25 minus minus plus 1 upon 25. Solve this, we have 0.5 in bracket 2 upon 25. Solve this, we will get 25 centimeter. F is equal. This is the focal length. When we solve this, we will get the focal length. So focal length of given double convex or biconvex lens whose radius of curvature of each surface is 25 centimeter and refractive index of the material of the prism, sorry, lens is 1.5. Now see one more problem by the same way. In next problem we have to calculate the focal length of plano convex lens. Instead of biconvex we have to calculate the focal length of plano convex whose one side is plane, one surface is plane while other surface is convex. So this is plano convex lens, and in the problem we have given the refractive index of the material of the prism, that is 1.5, same, and one side is plane, so this is infinite, and radius of curvature is same, 25 centimeter. So this is the given data. R1 is equal to infinity, R2 is equal to 25 centimeter, and refractive index of the material of the prism is 1.5. I am again going to read the problem, or the problem is very simple. Calculate the focal length of a plano convex lens for which the radius of curvature is 25 centimeter. For which the radius of curvature is 25 centimeter. That means the radius of curvature of this curved surface is 25, and the one plane surface is having radius infinite. Okay, and the material of refractive index of the material of the prism is 1.5. So again substitute the value in the same problem, same formula. We have 1 upon f is equal to mu minus 1, that is 1.5 minus 1, in another bracket 1 upon infinity minus 1 upon 25 minus 25. Okay, solve this. 0.5 in bracket 1 upon infinity, that is 0, minus minus plus 1 upon 25. So 0.5 into, or simply 1 upon into 1 upon 25, or 0.5 upon 25. It is need not necessary to use the calculator. 0.5 is nothing but 1/2 into 1 by 20 is equal to 1 upon 50. So 1 upon f is equal to 50. That means f is equal to 50 centimeter. This is the radius of curvature. Without using the calculator, we can find out the value of radius of curvature. Now the next problem. In next problem, a lens made up of a glass of refractive index 1.5. Again, refractive index of the material of the prism is given 1.5, and has two spherical surfaces. One surface is having radius of curvature 25 centimeter, and another radius of curvature 70 centimeter. See, this prism will be looking like this. This is the bioconvex, but both the surfaces are not having same radius of curvature. Two different surfaces having two different radius of curvature. One of the surface is having 25 centimeter radius of curvature, and the another surface is having 70 centimeter radius of curvature. Material of the prism, the refractive index of the material of the prism is 1.5. So substitute, consider here value as plus 25 centimeter is the first radius of curvature, 70 centimeter is the radius of second curvature, and refractive index 1.5. Again substitute the same value in the same given formula. 1 upon f is equal to 1.5 minus 1 in bracket 1 upon here second 1 upon what 25 minus 1 upon 70. Solve this. You will get the answer. F is equal to 7.7 centimeter. When you solve this bracket by using calculator, the answer will be the focal length of such convex lens having two surfaces with different radius of curvature, that is, so one surface having radius of curvature 25 centimeter and another surface is having radius 70 centimeter, as well as the material of the refractive index of this prism is what 1.5. Then when we substitute the value of R1, R2 and mu in the lens maker formula, we are having the focal length of such type of convex lens is 77.7 centimeter. Okay. Now we are going to see different type of problems. See here, all the problems which we studied up to this point are very important. Now next problem, we are having a complex system of two converging lenses having focal length f1 instead of radius of aperture. Now we are having two converging lenses. Up to this point we solve the problem regarding single convex lens. Okay, now here we are going to find out the equivalent focal length of a complex system. In a complex system we are having two converging lenses, that is two convex lenses. One is having focal length 15 centimeter and another lens is having focal length 20 centimeter, and these two lenses are placed coaxially 10 centimeter apart, that is x is equal to 10 centimeter. See here, suppose this is the first convex lens, this is the second convex lens, both the lenses are placed coaxially. That means what? Principal axis is same for both of these planes, L1 and L2. Focal length of first lens is 15 centimeter and focal length of second lens is 20 centimeter, and distance of separation between them is x. Now here we have to find out the focal length of equivalent lens. Okay, so here this is the given data. Now in order to calculate the focal length, equivalent focal length, we have f 1 upon f is equal to 1 upon f1 plus 1 upon f2 minus x upon f1 f2, or simply 1 upon f is equal to f1 plus f2 upon f1 f2 minus x upon f1 f2, or 1 upon f is equal to f1 plus f2 minus x upon f1 f2, or simply by changing the value of denominator and numerator, we have f is equal to f1 f2 upon f1 plus f2 minus x. Then substitute the value of f1 f2 and x from this data, given data. We having 15 into 20 divided by 15 plus 20 minus 10. We will having 15 into 20, 300 upon what? 15 plus 20. 25. So 12 centimeter. F is the equivalent focal length of the given complex system, or here we can replace these two lenses by a single lens which is having focal length 20 centimeter. Okay. Now here not only we have to calculate the focal length, but sometime the position of principal points may be asked. Then suppose this is the given data and this is the equivalent focal length of the given complex system which is having two convex lenses L1 and L2, and these two lenses are separated by a distance 10 centimeter. Okay. Now what will be the first principal point P1 and second principal point P2? Just we obtain the derivation in previous lecture. So value of P1, position of P1, that is alpha is equal to x f upon f2. This is the formula for the position of this principal point P1 with respect to this lens. So x is what? 10. Focal length is 12. What is value of f2 is 20. So 120 upon 20 is equal to 6 centimeter. So principal point P1 is at a distance 6 centimeter from L1. Similarly, we can calculate the value of, determine the position of P2 with respect to L2, and this is nothing but beta is equal to minus xf upon f1. Again here substitute the value of x as 12, f is 12, 10 centimeter, upon 12. Again f1 is 15. So solve this, minus sign, because B is situated, or principal point is situated toward the left of the second length, so it is negative. So it will be 120 minus 120 upon 15 is 8 centimeters. So principal point P2 is situated from second length at distance 8 centimeter. Negative sign is due to, as per sign convention, P2 is situated to the left of the L2. Okay. Now next problem. Again, by the same method, we are going to see different problems with the same system. Now consider next problem, a thin converging and diverging lens. Now instead of using converging lens and diverging lens, here two lenses are used, but one of them is converging and another is diverging, or one of is convex and another is concave. Instead of both the convex, one of them is concave. These two lenses are placed coaxially. Placed coaxially means what? The principal axis of this lens and principal axis of this lens are one and the same. The distance of separation between them is 6 centimeter apart. Distance is given. Now focal length of each lens is 10 centimeters. So f1 is 10. Second one is diverging. So focal length is minus 10. Why minus? Because second lens is diverging lens or concave lens. Hence its focal length is minus. Distance of separation x is equal to what? 6 centimeter. Now here we have to find out the equivalent focal length and then position of principal point. So what will be the focal length? F is equal to f1 f2 upon f1 plus f2 minus x. Substitute the value 10 plus minus 10, not plus, into, upon 10 plus minus 10 minus 6. 10 into minus 100, 10 into minus 10, upon this thing cancel with each other, minus 6. So only 100 by 6 is equal to 16.66 centimeter. This is the equivalent focal length of this combined system. Now we have to find out the position of principal point P1 and second P2. This is L1 and this is L2. What will be the position? P1 is equal to P1 alpha is equal to, what is the formula? Alpha is equal to x f upon f2. Then substitute x is nothing but 6 centimeter, f is 16.66 upon value of f2 is minus 10. So solve this, we will get answer minus 9.9 centimeter. Similarly, we will find out the position of second principal point P2 with respect to L2, that is beta is equal to x f upon f1. X is 6, f is 16.66, and value of f1 sorry okay is 1 okay minus sign, so x minus and it 10. So again solve this, the answer will be minus 9.9 centimeter. So at equal distance, this distance of or position of P1 with respect to L1 and position of P2 with respect to L2 is same, that is P2 and P1 are situated at distance 9.9 centimeter with respect to L1 and L2 respectively. Okay. Now we are going to see next problem. Next problem. Here two thin convex lenses. Again there are two thin convex lenses. This one and this one. Both are placed coaxially. Focal length of first convex lens is 15 centimeter and second one is 30 centimeter. So f1 is equal to 15 and f2 is equal to 30 centimeter. And distance of separation between them is simply 20 centimeter. They are up plus 20 centimeter apart from each other. So x is equal to 20. Very simple problem. Now we have to find out the equivalent focal length of a given combination of lenses. Equivalent focal length of the given combination of lenses, and this is nothing but f is equal to f1 f2 upon f1 plus f2 minus x. Substitute the value from given data, 15 into 13, okay, upon, just I want to check what will you get, then 15 plus 13 minus 20. Solve this, you will get the answer. The answer will be what? 18 centimeter. In this way you can solve number of problems regarding to geometrical optics. In next lecture we will start the second chapter. Till then we shall stop here. Have a good day. Thank you.